So in the last chapter, we will study the application of catalysis in organometallic chemistry. That means we have a reaction A plus B in the presence of organometallic catalyst that gives C plus D. We have to propose a convenient mechanism. This is to write the steps of the reaction, and we studied till now about 13 mechanisms. To note that we cannot prove that this mechanism is 100% correct. I can know or I can choose one of the steps which is incorrect. That means we have inconvenience in the mechanism. So the history of the industrial catalytic process, and we have international names or notations for these reactions. For example, the cracking, we use platinum rhenium catalyst supported on alumina. We have alkylation, we have hydrocracking, we have hydrodesulfurization. We use the MO and CO oxide catalyst. So these are the international industrial catalytic process. And now we want to choose some of this industrial process in order to predict or to propose a convenient mechanism. First of all, what is the definition of a catalyst? A catalyst is a substance added in very small amount in order to make a non-spontaneous reaction spontaneous. Or if the reaction is spontaneous, adding catalyst will increase the rate of the reaction and will increase the rate of the reaction to reach the equilibrium. So the equilibrium constant of a reaction is not affected by the addition of the catalyst. A catalyst will change or will define a certain pathway to pass from A plus B to C. We have two types of catalyst. Homogeneous catalyst, where 95% now of the chemical process use heterogeneous. What is the definition of homogeneous and heterogeneous catalysis? Heterogeneous catalysis is added to the reaction system A plus B, and the catalyst and the reaction system form more than one layer. So this heterogeneous catalyst will work on the surface of the catalyst. And at the end, by filtration, we can regenerate the catalyst and reactivate it in order to be reused. Homogeneous catalyst, when added to the reaction system, we could not distinguish several layers. So the homogeneous catalyst and the reaction system form one layer. In general, the homogeneous catalyst is more reactive than the heterogeneous, since the homogeneous catalyst is a real reactant, but at the end could not be regenerated. So most of the industrial organometallic process used heterogeneous catalyst. This is the reaction of hydrogenation of alkene to the alkene fragment, and we observe that by using by using the homogeneous catalyst, the yield is greater. So we have, for example, with rhodium, Cl, tris triphenylphosphine, the yield is 100%. Using heterocatalyst, this reaction has 0% yield. So the most important is to draw the catalytic cycle. A catalytic cycle consists of a sequence of the stoichiometric reactions, normally reversible. We studied that the opposite of the oxidative addition is the reductive elimination. The opposite of the ligand addition is ligand dissociation. So most of the reactions are reversible, and we can favor one direction on another according to the properties of the catalyst, and especially the electronic count or the electron density around the metallic center. So the catalyst, why this is a catalytic cycle? Since the catalyst should be regenerated, so it can participate in the cycle of the reaction several times. So how to draw the cycle? First of all, we use the catalyst. We should start by the catalyst. In some reactions, we start by pre-catalyst, which is not the active substance in the catalytic cycle. So we write pre-catalyst that decomposed to catalyst. This is the active catalyst. And then the active catalyst will react in order to do the catalytic cycle. Why we use a pre-catalyst? Some of the organometallic catalysts are highly sensitive, so they are not stable. If we use them directly, they decompose, for example. For this reason, we use a pre-catalyst substance that in course of the reaction system, it regenerates the active catalyst that will do the catalytic cycle. When we have arrow in this direction, that means this is a substance added. So the catalyst with the reactant A will give intermediate catalyst A. What is the nature of this intermediate? It depends on the nature of the catalyst used. So this reaction or this step should be one of the 13 steps we studied previously. And to note that the catalyst A intermediate should not be stable, since it should continue to give another intermediates. So if the catalyst A intermediate is stable, the reaction, the catalytic cycle, will be stopped on this step. So it should not be stable. Then we used the reactant A. The reaction is A plus B gives C. To note that in the catalytic cycle, you have to use a step. In a step, you have to use A. In another step, you have to use B. So now we used A. Then we add the reactant B. This is another step. We obtain intermediate catalyst A and B. Then this catalyst A and B will be transformed to catalyst C. Then the catalyst C will regenerate or will give the product C and regenerate the catalyst, and therefore the catalyst will continue again. So pay attention how to write the catalytic cycle. You start by the catalyst. In steps, you should add the reactants present A and B, and at the last step, you obtain the product C. In most cases, the product C is obtained by reductive elimination or by dissociation. So the reductive elimination is always at the end of the catalytic cycle. The reactant A and reactant B are added in the catalytic cycle most at the beginning or in the middle. And the mechanism proposed or the step proposed is always oxidative addition or ligand addition. So oxidative addition is always at the beginning, reductive elimination is always at the end. We have some definitions for good catalysis. The intermediates must have short lifetimes. That means the intermediates should not be stable in order to continue the catalytic cycle. In organometallic chemistry, we define tone, which is the turnover number. The catalytic turnover number, tone, is the number of moles of products per mole of catalyst. It indicates the number of catalytic cycles. For example, we can say after 2 hours, the tone is 2,400. What is the meaning of 2,400? To know that the tone is the number of catalytic cycles or is the number of mole of products per mole of catalyst. That means if you have tone 2,400, using 1 mole of the catalyst, you obtain 2,400 moles of product. 10 mole percent catalyst in the organometallic terminology, we write, for example, we use 10 mole percent catalyst. That means the turnover is equal to 10. So these are definitions. The catalytic turnover frequency, which is the TOF, is the number of moles of product per mole of catalyst per unit time. To note that as tone is higher, that means your catalyst is very efficient. So in organometallic reactions, we search to have high number of the tone, of the turnover number. So the number of turnover performed more is better. The TOF, turnover frequency, faster is better. Good selectivity for the product. This is one of the most important problems in organometallic reactions. Generally, the organometallic reaction A plus B that gives C plus D are the major products. And in this reaction, we have subproducts and we have to propose the mechanism that lead to this secondary products. Another problem is the regioselectivity or the enantioselectivity or the chemoselectivity or the formation of isomers. Why we use organometallic? Why use organometallic in catalysis? What is the importance of the organometallic complexes? First of all, we can add a wide range of ligands. Suppose you want to introduce a ligand L on organic fragment. So the main strategy is to add this fragment to the organometallic complex, then to add the ligand L to the catalyst, to the structure of the complex, and by reductive elimination, you can regenerate or you can form the organic fragment and the ligand L in one product. So the importance of the organometallic complexes is that you can put any ligand you want on the structure of the complex. Second, the organometallic complexes of transition metals, the transition metals have several oxidation states. For example, if you have platinum that can be transformed easily to platinum 2, so the oxidative addition is easy. Due to the stability of several oxidation states, the organometallic complexes of transition metals are very important. We have also the geometry of the complex. Suppose we want to obtain a fragment. Suppose we want to obtain a trans fragment, so we can use bulky organometallic complexes where the addition of the ligand to the other fragment is not possible from one side and is possible from the second side. So if it's not possible from one side and is possible from the second side, so we can obtain only one isomer, for example, trans and not cis. So this is important characteristic of the organometallic complexes. Now we pass to the catalytic cycle. This is the hydrogenation of alkene to alkane. And we use the Wilkinson catalyst, which is well known, the rhodium Cl tris triphenyl phosphate. To note that in one step should appear the addition of alkene. In another step should appear the addition of hydrogen, and in third step should appear the formation of the alkane. The common mistake of the student in writing the organometallic mechanism, sometimes the student forget to add one of the ligands, so the mechanism is incorrect. We have to start by the catalyst. Usually we start by the catalyst. And when we write the catalytic cycle, to note that for any intermediate obtained, you should count the electrons in the complex and you should determine the oxidation state of the metallic center. For example, I start with the catalyst. This is rhodium 1, okay, and the rhodium 1, the rhodium 0 is rhodium 0. The rhodium 0 is D9. So the rhodium 1 is D8. Phosphine is 2 electron donor, 2, 4, 6, 8. This is 18. This is 16 electrons. So I determine the oxidation state and I determine the electronic counting. I have to add hydrogen in one step and alkene in another step. The student, for example, can write the first step is the ligand addition of alkene. Another student can write the first step is the addition of hydrogen molecule. the addition of hydrogen molecule is the oxidative addition. If the student write the addition of alkene, this is ligand addition. And pay attention that the complex is 16 electrons. So the alkene addition is possible and the complex obtained is 18. And the oxidative addition is always possible since the complex is D2 or greater. Okay, and we have vacant site. So I start with the first step, which is the oxidative. This is the oxidative addition. And I will put rhodium 3, and this is 18 electrons. If the student write oxidative addition, and I did not see that he changed the oxidation state of the metallic center, so this is incorrect step. Rhodium 1 to rhodium 3, oxidative addition, and we increase the electronic counting by 2. Now we have a complex which is saturated. So I used this first reactant. We have saturated complex, and I want to add the alkene. It's impossible to add the alkene before dissociating a ligand. So, what is the ligand that can be dissociated? First of all, it can dissociate Cl, or it can dissociate, for example, triphenylphosphine. I have two possibilities. When Cl is dissociated, it should be replaced by an anionic ligand. But in the reaction, we have neutral ligand. So it's preferred to lose triphenylphosphine and to add alkene. So the student can write ligand dissociation, p-phenyl 3. If I ask him, what is your reasoning to dissociate this triphenylphosphine, he can say this is a bulky group. Okay, then the student will write ligand addition alkene. This is identical if he write ligand substitution, and the substitution is in the dissociative pathway since the complex is saturated. So we have ligand addition, then ligand dissociation, then ligand addition, or simply we have ligand substitution. And in the substitution, we replace one ligand by another ligand of the same nature. In some exercises, we have indication that the oxidation state did not change or the oxidation state of the metallic center has been changed. So in this example, this is a ligand substitution. We obtain rhodium. Pay attention. You should not change the oxidation state. We obtain rhodium 3, 1, 2, 3. And the complex is always 18 electrons since this is a substitution. Okay. Pay attention that we have alkene that should be transformed to alkane. That means we have to break the double bond. The double bond or the unsaturated bond is broken in organometallic chemistry by one simple reaction, which is the migratory insertion. And to note, in the migratory insertion, one anionic ligand will attack, one anionic ligand on the complex will attack another unsaturated ligand on the metallic center. So now we have migratory insertion, H to alkene, and always after the migratory insertion we open a vacant site. And if this vacant site is not occupied by trapping ligand, the reaction will shift backward, so in the direction of formation of this intermediate, and the reaction system will be stopped. So always after the migratory insertion, we have ligand addition. What is the ligand that was added? The ligand that was added might be one of the ligand dissociated, since the dissociated ligands are in the reaction system. Or it can be one of the reactant present. So the ligand addition might be alkene, might be hydrogen, or might be one of the ligand dissociated. To note that in this case, we have triphenylphosphine, which is a bulky group that is dissociated, but still in the reaction system, so it can be used directly as trapping ligand. So ligand addition phenyl 3. This is a trapping ligand. It's preferred after the migratory insertion to use a trapping ligand. So we have two possibilities. The hydrogen can attack this carbon, or the hydrogen can attack the second one. But since the alkene is symmetrical, so if attack carbon 1 or carbon 2, this is the same product form. So we have only one possibility. So we obtain alkyl chain. This is migratory insertion ligand addition, and the complex is -1. This is rhodium 1, rhodium 3, and the complex is rhodium 3. That means 6, 2, 4, 6, 8, 10, 12. This is 18 electrons. The migratory insertion, when it opens the vacant site, and the vacant site is occupied by the trapping ligand, the electron counting would not be changed. So we obtain this intermediate. Now we have to regenerate the alkene. The hydrogen, which is H minus, and the alkyl, which is R minus, will do what we call reductive elimination, RE, to regenerate or to form this product. And if we lose these two ligands, we obtain the same initial catalyst, and therefore the catalytic cycle will start again. So this is the catalytic cycle we propose. Do we have other possibilities? Yes. I started with the oxidative addition. The student can start theoretically by the ligand addition, by the alkene ligand addition. In this reaction, they mentioned that we have alkene isomerization. We have alkene isomerization when the alkenes we start with is non-symmetrical. So now, what is the key step in the alkene hydrogenation? The key step is the migratory insertion that form the alkane fragment from the alkene reactant. Suppose they mentioned the formation of isomers. We have alkene isomerization. Suppose we start with alkene in position 2, we obtain the double bond in position 1. So R, double bond, CH3, 4, R, and the double bond is in position 1. This is isomerization. They ask to mention or to propose the mechanism of this reaction. Suppose the complex is ruthenium and we have alkene, so the first step is ligand addition. Then we have migratory insertion. The hydrogen attack anti-Markovnikov rule, so the hydrogen will attack the more substituted. Okay, so we obtain, or the more substituted. In this structure we have R. Suppose we have hydrogen in this case, so if we have hydrogen, the hydride will attack the most substituted. Okay, the mechanism is given, so we have migratory insertion. We obtain this structure. Pay attention that we have alpha carbon and we have beta carbon, and always we have hydrogen in this methyl. Okay, so the inverse of the migratory insertion is the hydride elimination. If we have beta hydride elimination, okay, we obtain this. This is beta position and this is beta position. So we have possibility to eliminate this hydride. Why? The hydrogen of the methyl group is easier than this hydrogen. First of all, it's close to the metallic complexes. So we obtain this structure, and pay attention, in this structure, okay, appears the double bond in position different from the initial alkene. Then by ligand dissociation we obtain this structure. So what is the key of the alkene? When you have alkene hydrogenation, you think directly about the migratory insertion. When you have alkene isomerization, you think directly by the key step, which is the beta hydride elimination. So beta hydride elimination, alkene isomerization, migratory insertion, alkene hydrogenation. We pass to the third mechanism, which is the alkene hydroformylation. Alkene, in the presence of hydrogen gas and CO gas, will give aldehyde, linear chain, and branched aldehyde. So pay attention. We have, this is carbon 1, carbon 2, carbon 3. So we have 1, 2, 3, and we add a new fragment, which is the COH. This fragment can be added on carbon 3. This is the linear 4, or can be added on carbon 2. This is the branch 4. So this is linear and this is branched. So we obtain two products. One of the products is major, the second is minor. And in this reaction, They mentioned, for example, the formation of byproducts, alkane, or byproducts, alkene isomerization, alkene isomers. So, directly, I can know the catalytic cycle of formation of alkane from alkene. Since we have hydrogen and we have catalyst, so this is hydrogenation reaction. So the alkane is formed by hydrogenation reaction studied previously. And when we have hydrogenation reaction, we have in the steps, the key step is the migratory insertion. And the inverse of the migratory insertion is the beta hydride elimination, so we can explain the alkene isomers. So the byproduct, the alkane, is formed by the same mechanism proposed by Wilkinson, and the alkene isomer is formed by the catalytic cycle, where the key step is the beta hydride elimination. So we explain the formation of the byproducts. Now we have to explain the appearance of the carbonyl functional group CO. So we start with the 3 carbons, for example. We obtain a structure of 4 carbon chains. We add 1 carbon and we add 1 oxygen. For this reason, this is the hydroformylation. The catalyst used is the cobalt. Another important characteristic is the nature of the catalyst. When you have ligand, when you have alkene hydrogenation, think about platinum and nickel catalyst. When you need hydroformylation, so the appearance of the functional group carbonyl, think about catalyst of type cobalt or rhodium. I will explain the mechanism. So we start with the catalyst. This is the catalyst we used. We start with. First of all, you have to define the oxidation state. This is cobalt. This is cobalt 1. The cobalt is D9. So this is D8, 2, 4, 6, 8, 10. So this is 18 electron complex. We have 3 ligands to be added: the alkene, the hydrogen, and the C. If we add, the hydrogen is added by oxidative addition. The alkene can be added by ligand addition. The carbonyl can be added by ligand addition. But the first step is not the oxidative addition, since this is 18 electron complexes. We don't have vacant site. And H2 is non-electrophilic substrate. In the non-electrophilic substrate, we need metallic center D2 or greater, and we need a vacant site. The complex is saturated, so we don't have vacant site. So hydrogen oxidative addition is not the first step. The second step, the second proposal is to add alkene. If we add alkene, alkene should replace one of the ligands present. And in this complex, we have, for example, carbonyl trans. We have the cis effect or the trans effect. So we can remove easily a carbonyl. So first of all, minus CO, this is a ligand dissociation to open a vacant site. To note that in your proposal of the mechanism, it's not necessary to mention the reasoning of the ligand dissociation. Why you dissociate CO? If you want to dissociate CO, directly do it. Okay? Do not justify. If they ask us why we have, for example, ligand dissociation, you can write this is a ligand dissociation to open a vacant site, and why you have ligand dissociation since the bonds are weak due to the cis effect, for example, or the trans effect. So we have ligand dissociation, we open a vacant site. This vacant site should be replaced directly by the ligands presence. What are the ligands present? We have CO. It's impossible to dissociate CO and then to replace CO. So this is not ligand addition of CO. You have H2. H2 could not be added simply to a vacant site. H2 is added by oxidative addition. So this is not the case. Okay, so you have only one alkene added. You have directly after the ligand dissociation and the open vacant site, you have alkene, which is the ligand addition. So in total, you can say that is ligand substitution of CO by alkene. We obtain this structure. Okay. Now we have two possibilities. Hydrogen can do migratory insertion on CO, or hydrogen can do migratory insertion on alkene. Hydrogen to CO form one product. Hydrogen to alkene will form two products since the alkene used is non-symmetrical. The affinity of hydrogen to alkene is greater than the affinity of hydrogen to CO. So we have, in this case, we have migratory insertion H to alkene. 2, we open a vacant site. Directly, the vacant site should be occupied by a trapping ligand. What is the trapping ligand? In this case, we have CO that is in the reaction system, and from the beginning we have CO added. So this is a ligand addition C. We obtain this structure 1, 2, 3, 1, 2, 3. This is, for example, the CO added, and the migratory insertion H to alkene will form alkyl fragment. But pay attention, we have another possibility, which is the CO, the cobalt, CO, CO, carbonyl, and here we have carbonyl. And pay attention, the hydrogen should attack the most substituted. This is anti-Markovnikov rule, since the hydrogen in this case is hydride. So it will attack the carbon bearing R, and the bond is between cobalt. I will note this is carbon 1, and this is carbon 2. So the bond is between cobalt and carbon 2. Cobalt, carbon 2, and this is the carbon 1 bearing the R group. This is the first possibility, and this is the major, since this is anti-Markovnikov rule. But we have another possibility that the carbon, the hydrogen, attack the carbon 2. If the hydrogen attack the carbon 2, the bond will be between carbon 2 and cobalt. So we obtain R, hydrogen attack carbon 2, and we obtain this structure. This is carbon 2, and this is carbon 1, and we have the hydrogen on carbon 1. So now if you look, we have appearance of two fragments, one which is linear, and the second is branched. So this is the major, and this will be the minor, since this is the Markovnikov rule, and the anti-Markovnikov rule is major. Now we have, pay attention, you should transform, you should appear AC double bond O. AC double bond O is appeared in one case. You have R minus that attack carbonyl group in order to form RC double bond O. So we should have a migratory insertion. Now we have, this is the alkyl, this is the alkyl fragment, and we have CO. So we will have attack alkyl on CO. This is one migratory insertion, okay, alkyl on CO. And second, pay attention, we need a trapping ligand. What is the trapping ligand? The trapping ligand is the CO added continuously in the reaction. So we have ligand addition CO. We obtain 1, 2, 3, 1, 2, 3. The vacant site we open is occupied by CO, and we obtain this fragment, which is the result of the migratory insertion of the alkyl to CO group. So this is migratory insertion, then ligand addition. Now the alkene has been added, the carbonyl has been added. Never forget that you have always hydrogen from the beginning. So you have to use hydrogen. The hydrogen is used by oxidative addition. But if I count this complex, this is a cobalt 1. Cobalt 1 is the 8. 2, 4, 6, 8, 10. So this is 18 electrons. If I want to add hydrogen by oxidative addition, the reaction now is practically impossible, since the complex is saturated. So what to do? First step is to do ligand dissociation, is to dissociate one of the carbonyl to open a vacant site, then to add hydrogen by oxidative addition, and now I used the hydrogen. So we obtain the hydrogen, we lose CO, this is the CO that has been lost, and we obtain 2 hydride in cis position. Okay, this is hydrogen and hydrogen. Then by reductive elimination, we remove the H minus with the R minus to form this structure, which is the first product. This is the major product. Why this is the major? Since it has been formed from the major intermediate. If you repeat this catalytic cycle by following the same steps, but you change only this step, instead of the alkyl, normal alkene, you use the branch alkyl, and we will obtain the second branch product. So this is a reductive elimination that will regenerate the initial starting catalyst, and then the catalytic cycle will go on. Okay, so this is the mechanism of the reaction. And pay attention, in some exercises they ask to explain the formation of all products formed. If you have 3 products formed, that means you have to write 3 catalytic cycles. If you have 2, you write 2. Or you can say that the formation of the branch product will follow the same mechanism, but by using this intermediate, and you draw the intermediate. For me, this statement, when you write the statement, so you answer correctly the catalytic cycle. So you have 2 choices, or you write the formation of the byproduct by writing another catalytic cycle, or you mention by a statement the formation of this product. And do not forget that from the beginning we explained the formation of the alkane byproduct by the same mechanism of Wilkinson. This is the alkene hydrogenation. Since we have hydrogen with alkene in presence of catalyst will do hydrogenation reaction. And when we have hydrogenation reaction, we have one of the steps, which is the migratory insertion. So the opposite step, which is the beta hydride elimination, will explain the formation of alkene isomerization. This reaction explains the formation of acetic acid from methanol and CO. This is the Monsanto process.
Doctor?
The formation of methanol from carbonyl and hydrogen in presence of Fe catalyst. This is the Fischer-Tropsch industrial process. The decomposition of methane with water in the presence of nickel catalyst to form carbonyl and hydrogen. This is the syngas process. So they ask, for example, to write catalytic cycle for each reaction. I will do only the Monsanto, the formation of acetic acid. The formation of acetic acid is the following reaction. Methanol plus CO in the presence of catalyst, rhodium catalyst, and in presence of bi-catalyst or of co-catalyst HI that form CH3 COOH. This is the formation of acetic acid from methanol by carbonylation. Okay, so what is the mechanism proposed? I will write the steps. First, you have to write your catalytic cycle. This is the catalytic cycle. Second, you will start initially by your catalyst. Okay. So you start by catalyst. You obtain intermediate. I will see if we have another intermediate. We have another intermediate. Okay. This is a catalytic cycle. So the catalyst used is rhodium I the catalyst used is given CO and the catalyst is minus. So the reaction is CH3OH plus carbonyl that will give CH3COOH, and the catalyst used is rhodium and the co-catalyst is HI. So what is the role of HI? How to think, or what is my strategy in order to find the catalytic cycle? First, I should add CH3OH. Adding CH3OH, CH3OH. So I have only one possibility, which is the ligand addition. And you know that the oxygenated ligands, I explain, it's not necessary to write this in your catalytic cycle. I am analyzing the strategy to find the catalytic cycle. So the oxygenated ligands are weak donor. We studied this in chapter 2. So they could not be added easily. For this reason, we add HI. Why? Since CH3OH plus HI give CH3I plus H2O. So CH3I is electrophilic substrate that can do oxidative addition easily. So this is the role of HI. The role of HI is transform CH3OH to CH3I that can be added easily. So reaction 1, I have now CH3I in my reaction system. So the first step, the catalyst is rhodium, is ML3X. M. Okay. So what is the nature of the catalyst used? I will search CH3. So this is rhodium I2 CO2. Then the catalyst used is given is rhodium I2 CO2 minus. So we have CO and we have CO. Okay. This is rhodium X minus 2 equal minus 1. So X equal 2 minus 1. This is rhodium 1. The rhodium 1, the rhodium 0 is D9. So the rhodium 1 is D8. D8, 2, 4, 6, 8, and 8. So this is 16 electrons. The oxidation state and the electronic count should be mentioned in your catalytic cycle. The first step is oxidative addition. CH3I. So I add the first reactant. Oxidative addition, we obtain rhodium 6. This is CH3, for example. This is I. This is CH3. And we have initially 2 carbonyl and 2I. The geometry is not important. So this is rhodium 3, 18 electrons. The first step is oxidative addition. We have appearance of carbonyl. The appearance of carbonyl is possible only when you transform the C triple bond O to C double bond O, and the C triple bond O to C double bond O is possible if you write the migratory insertion. The question now, do we have migratory insertion? Yes. This is R minus that can attack the CO. So we obtain rhodium I CO CH3, and we have CO and we have I, and pay attention with the appearance of the vacant site. So this is 1 is migratory insertion. We open a vacant site. The vacant site should be filled directly by one of the ligands. What is, do we have a ligand that is formed in the reaction system? No. Do we have ligand initially? Yes, I have CO. So if I put 2 ligand addition CO, I will keep it. You will write now ligand addition CO, and it will be filled in the vacant site. So we obtain, or you can write it in the same step. You can write migratory insertion to ligand addition. So this is the CO that should be added. And we have CO in the vacant site. So this is the CO, and we have appearance of the CO CH3. Okay, so migratory insertion, then ligand addition CO. Pay attention that we have to regenerate rhodium I2 with 2 CO. Rhodium I2 with 2CO. So we have another step is the step that will regenerate the initial catalyst. Okay. If we do migratory insertion, if we do reductive elimination, that means we have to remove CO rhodium. This is the first I. This is the second I, the CO, the CO. This is 2I. And we have 2CO. This is 1CO and the second CO. So the reductive elimination is CH3O with the I minus. Pay attention in the reductive elimination when we add, in the oxidative addition, we add XY. So we obtain MX, MY, and XY are two anionic ligands. So this is I minus anionic, and this is CH3CO minus, this is anion. So this reaction by reductive elimination will give the CH3COI, okay, and will regenerate the initial catalyst. But we did not obtain CH3COH, we obtain CH3COI. So we did not obtain the product we need. Do not forget that in your reaction system you have water formed by the addition of HI to CH3O. So CH3COI in the presence of H2O present, so this is hydrolysis, will regenerate the CH3COOH plus HI, and this HI will be reused at the starting of the catalytic cycle. Do not forget that your catalytic cycle starts by the mechanism of HI. HI transform CH3OH to CH3I. By oxidative addition, we can add CH3I. So HI is the key at the starting of the catalytic cycle, and HI is a co-catalyst, so it should be regenerated. And if we write the hydrolysis of CH3COI, we obtain CH3COH, which is the acetic acid, plus HI. This HI will play the role of the co-catalyst at the starting, so we have regenerating of the catalytic cycle. So these are the steps proposed in the Monsanto process. We pass to another reaction, which is the hydrogenation of alkene. Alkene plus HCN in the presence of catalyst to give HCN. Suppose I write this reaction in traditional organic. R plus HCN in organic. The hydrogen is added to the less substituted. So you should obtain R and you obtain the Cn on the most substituted. So you obtain the opposite of your product when you use organometallic catalyst. This is the importance of the organometallic catalyst. We obtain the opposite of the Markovnikov rule. Why? Because in the catalytic cycle, in the catalyst, when we have hydrogen, when we have metal hydride, the hydrogen is H minus. So this hydrogen will attack the carbon the more substituted. So we have in the catalytic cycle the anti-Markovnikov rule. For this reason, we obtain the second product. The catalyst used is nickel catalyst. This is nickel 2. The nickel is D10. So this is D8, 2, 4, 6, 8. This is 16 electrons. Pay attention that we should add alkene, we should add HCN. The alkene is added only by one possible mechanism, one possible step, which is the ligand addition. The HCN could be added only by oxidative addition. So in your mechanism, on the draft, you know that you have ligand addition alkene and you have oxidative addition HCN. This is from the starting. Okay. So first of all, I have to write the mechanism. Alkene, I have open site, I have vacant site. So the student can write first is ligand addition, and the ligand addition will give an I, L, H, Cn, L, and we have addition of the alkene. This is R. This is ligand addition. And the complex in this case is Ni2. This is Ni2, 18 electrons. So this is the first step, ligand addition. The second step is to add HCN. When we add HCN, the HCN could be added only by oxidative addition. And the condition of the oxidative addition, the metallic center should be greater, D2 or greater. This is the case of nickel 2. And should have a vacant site. This complex is 18 electrons. Okay, so it could not be added. So we have to dissociate. The second step is L ligand dissociation of L. We can write two steps, or we can write directly. This is the ligand substitution of alkene by the ligand substitution of ligand L by alkene. So we obtain this structure. The nickel is nickel 2. And the complex is 60. We have, therefore, the reaction is the addition of HCN to break the double bond. And the double bond can be broken only by one possible step, which is the migratory insertion. Do we have a migratory insertion in this case? Yes, we have H minus and we have Cn minus, okay, and we have this neutral alkene. So we have two possibilities. H minus can attack alkene, or Cn minus can attack alkene. We know that the ability of H minus to alkene is greater than of Cn minus to alkene. It's not necessary to know this characteristic. In your reaction, you need H on the double bond. So it's necessary migratory. One is migratory insertion. H to alkene, and 2, which is the opening of the vacant site, so you should add a ligand. What is the ligand added? The ligand added is one of the ligand in the reaction system. So here we have L in the reaction system, and we can add HCN or we can add alkene. But if we add HCN or alkene, we complicated our reaction system, so it's easier to add the ligand L. So we have ligand addition L. We obtain 1. Okay, so we need another L 2 H attack, so we have 2. Okay, then we need a ligand L, so we have L on the side. Now this is minus and this is minus. Okay, migratory insertion. Here we don't have L. We have 2 ligand L. When we remove L, so we don't have L. When we add, okay, so reductive elimination. By reductive elimination, we form the product we need and we regenerate NiL2. Okay, by oxidative addition, we obtain this catalyst. So the starting was NiL2 and not NiLHCN. The starting is NiL2, which is the oxidative addition. So what are the steps? First, oxidative addition HCN. Second, ligand addition alkene. 3, ligand dissociation L. 4, MiH to alkene. 5, ligand addition L. 6, which is the reductive elimination. So suppose we have 6 steps, the grade will be 12 points or 18. If the student write, for example, 3 mechanisms, 3 steps, 3 correct steps, 3 times 2, he will get 6 points of the full grade 12. I pass to another important reaction, which is the coupling reaction, well known in organic. Rx plus R prime M. We have coupling R with R prime and formation of XM. So this is the coupling of 2R fragments in the presence of palladium. What is the palladium catalyst? The catalyst used is palladium PDL2. How to add Rx or how to add R prime M? Pay attention that small m is a metal. Is a metal fragment. Okay, so this is Kumada. When you use M, zinc, Negishi, thin steel, and when you use boron, this is the Suzuki process. These reactions are well known in organic chemistry. So the starting catalyst is PDL2. What are the steps to add? First, I have to add Rx. Rx can be added only by oxidative addition. R prime M is another mechanism different. So the first step is Rx. I obtain Rx. This is the oxidative addition. Okay, then pay attention. This is palladium X R, and we have L2, and we add M R prime. When M is added, M R prime is added to the catalyst, we obtain what we call a four centers, four bonds. We obtain interaction between, and pay attention that the palladium, due to the size, okay, and to some electronic properties, the palladium is a trans to the second metal M. So for this reason, this is a trans. Okay, and when we have formation of four bonds, four centers, we break this bond, and we have formation also of intermediate bond. So we break this bond, and we break the R prime M bond, and we obtain what we call this metallocycle, where the two metallic centers are in trans position. This is what we call a transmetallation, or we can call this is a cyclization. Cyclization, that means the formation of cycle. Then we have reversion of the bond. We have cycloreversion. Cycloreversion, so the palladium, this bond, will be between M and the bond between palladium and R prime. This is first cyclization, second cycloreversion, and we obtain R L2 R prime, okay, plus MX. So we have MX released. Then by reductive elimination, since this is R minus and R prime minus, by reductive elimination we obtain R prime, and the catalytic cycle will start again. So the first step is oxidative addition, the second is a transmetallation, and the third is reductive elimination. This is the explanation of the famous coupling reaction known in organic chemistry. So these reactions are the same. You can try to solve or to write the catalytic cycle, then to see the solution. I pass to the last mechanism, which is the metathesis of alkene. The metathesis of alkene is very important reaction that we have two different alkenes, and these alkenes are combined together. So we break the first, we break the second, then we join one fragment with another fragment, so we obtain R1, R2 alkene plus ethylene. And this reaction was discovered by Chauvin in 1971, and he got the Nobel Prize in 2005. So what is the mechanism used? First of all, we have metal alkene or metal carbene, metal alkylidine or metal carbene. Okay, this is the initial catalyst. We have to use ligand 1 and ligand 2. Ligand 1 or ligand 2 can be added on the metallic center by ligand addition if we have normal complexes. But in this case, we have the metal carbene or metal alkylidine. So what is the first step? The first step, we have double bond and we have R1. So we break the double bond. We break the double bond in the metal alkene and we form what we call the intermediate bond, M. So this is as previously, which is the formation of cycle. So we have formation of cycle. We can call it, we can note it cyclization, or this is the addition of a ligand by formation of cycle. So we obtain what we call the cycloaddition. We have formation of cycle and we have addition of the ligand. So we obtain this structure. Then we have the cycloreversion. So this is the bond and we have formation of alkene. This is the cycloreversion to obtain the new metal carbene. This metal carbene is different from the initial metal carbene. Then we redo the cycloaddition and the cycloreversion. So we obtain, by cycloaddition, we obtain the structure, and by cycloreversion, we obtain this double bond. And so we obtain the alkene and we regenerate the initial metal carbene. So what is the key of this reaction? The key of this reaction is first the formation of the cycle by addition of a ligand, which is the cycloaddition. Then we have cycloreversion, cycloaddition, cycloreversion, and reductive elimination. No, only we have cycloreversion. By cycloreversion, we obtain, by cycloreversion, then we have ligand dissociation. So this is formation of cycle with the addition of ligand. This is destruction of the cycle by ligand elimination. So this is the cycloreversion. Okay.